Okay, so we're going to start our digestive system lab. I did post online basically what we would see in the cadaver. So you want to make sure that you look at that also, as well as the histology slides that complement the lab as well as the lecture. So starting off, when we look in the abdominal pelvic cavity, this cavity actually houses a large number of different organ systems, including the digestive system. But you'll also see urinary structures, reproductive structures, lymphoid structures. In addition to the digestive system, there are many other organ systems that reside within the abdominal pelvic cavity. But by far and large, the digestive makes up the majority of organs that exist within this large space. Remember from our very first lab that cavities are body spaces that are lined with serous membranes that house organs, and we definitely have a very large cavity, the ventral body cavity, divided up into thoracic and abdominal pelvic. And in the abdominal pelvic, we're going to find that the dorsal body wall is lined with the parietal peritoneum, and then all of the organs are going to be covered with that visceral peritoneum. Just in general, remember serous membranes are the epithelium and underlying connective tissue that line body spaces that are never exposed to the outside. One of the major functions is to cause them to or allow them to be lubricated so that they can move with less friction within that body space, not only against each other, but the inside of the body cavity wall. We're going to find that these serous membranes are going to basically come off of the dorsal body wall, come out to the organs, cover the organs, and then go back to the dorsal body wall. So what we're looking at in this drawing is essentially the large intestine, which we can see here kind of coming up the right side of the body, going across from right to left, and then down the left side. We can see all of the small intestines here kind of hanging down and below. And then this yellow sort of tissue here with blood vessels within it, that's essentially a serous membrane. It's double-sided, and when it's double-sided, we'll refer to it as a mesentery that function to cover and surround all of these loops of small intestines and large intestines. They're going to function to allow blood vessels and nervous tissue out to the organs and back, um, and then again secure these organs to the dorsal body wall. So we're going to look at mesenteries. I talked about these in the lecture as well, but mesenteries are the double layers of serous membranes that extend from the body wall. It's always going to be dorsal because this is where we have our stable point of attachment, that being the spinal cord or the spinal column. And we're going to go out to the organs and then back again to that dorsal body wall. So when we look at mesenteries, this is a really nice simplified drawing. Remember, the serous membrane is just the epithelium. It's a simple squamous epithelium and the underlying connective tissue. That serous membrane is continuous. We just simply change its name depending on whether or not it's lining the body wall or if it's covering an organ. So if it's covering an organ, we call it the visceral peritoneum. So this is the visceral peritoneum, right? This is a little loop of intestine. And if it's on the body wall, we call it the parietal peritoneum. Okay, so this is just simply a serous membrane. So it's going to be allowing connective tissue fluid to ooze across it. That's called transudate or serous fluid, and it allows them to be nice and slippery. But to go from the parietal peritoneum out to the visceral peritoneum, you have to have this continuation. It's just really the same membrane. We just simply change its name depending on where it is. And so we're going to go out to the organ, we're going to go around the organ and back to the body wall. And where we have these double layers of serous membranes, like right here, there's two layers, we refer to this as a mesentery. So anytime you see the serous membrane kind of fold back on itself, like we see here, we call this a mesentery. Okay, so the greater omentum, which we'll talk about in just a second, looks like this, right? It's just this mesentery formed by two layers of serous membrane that kind of come off the organ. Okay, and here we can say the mesentery is functioning to stabilize the position of the organ. It also has connective tissue, most of which is adipose, in that space, which will allow for blood vessels and nerves to have a nice protected pathway to and from the organs. All right, so the mesentery's function, obviously there's several different functions. One, again, is going to be to stabilize these very mobile organs so they don't entangle within each other. Remember, you have about 20 feet of intestines, plus our small intestines, plus another 5 feet of large intestines, and they're all moving. They're doing this peristaltic motion, and they potentially can get entangled or twisted on each other. And so the mesenteries help prevent that. They also are going to be pathways or conduits for vascular tissue, right? Blood vessels and nervous tissue. So this is a really nice photo of small intestine. You can see it's kind of shiny here. So mesenteries are basically clear serous membrane. So it's like a nice slippery saran wrap. It's going to go over the organ here. So this would be the visceral peritoneum. When it comes this way, we'll actually have a counterpart serous membrane on the other side. And so sandwiched in between the two serous membranes are these blood vessels, which you can see here. They look black, but those are little blood vessels that have blood within them. And then in yellow kind of here, that's adipose that's sitting in between the blood vessels, helping to support them. And there's also be nervous tissue there as well as lymphoid tissue there. All right, so we're going to support the organs, we're going to prevent entanglement, we're going to provide conduits for blood vessels to and from the body wall. And so we're going to start to name these different mesenteries depending on where they are. The very first mesentery we would come across when we open up the body cavity is a mesentery called the greater omentum. The greater omentum we can see here in this cadaver drawing. It's attached to the greater curvature of the stomach, which you can see here, as well as the transverse colon. This portion right here, that's the transverse colon. It's actually going to be attached to that as well. And that just really just drapes down over the surface of the small and large intestines. If you grab this inferior aspect of it and then lift, it really is just like a sheet or a curtain that lays over it. So it's very easy to reflect it. So here you can see they've kind of lifted it up and laid it over the chest cavity or the thoracic cavity. It's the largest mesentery. It's filled with a lot of adipose, which we refer to as visceral fat. And it helps to enclose all that small intestines. It helps to insulate it and refine its motion. So I have here, it's easy reflected superiorly over the stomach without damage to it. It's filled with a lot of adipose tissue. It doesn't have a whole lot of vascularization because it's not going to the organs and systems. It's just simply overlaying them. Okay, so that's the greater omentum. Omentum means purse or bag. In some lower vertebrates, it actually goes down and it kind of creates a little cup here that really holds the small intestines. So if we had the opportunity to do cat dissections, we would see that. So that's why I called it the omentum, a little purse or a bag. This is looking at a cadaver image. So at this point, obviously the adipose is a little bit hard because it would be cold coming out of cold storage. But you can see there would be this really thick connective tissue, well, thick layer of adipose tissue enveloped within this sort of draping curtain of a mesentery. What they're going to do is take this bottom edge and lift it up. And when you do that, you can see here's the transverse colon that's attached to, as well as the stomach, which would be right above it. So you can kind of see this is the transverse colon here, and this is the bottom edge of the stomach. Okay, so when you lift this up, then you expose all of the intestines underneath. Okay. All right, another mesentery, which is referred to as the lesser omentum, is on the opposite side of the stomach. So this is a nice view of the stomach here. So it's a nice little J-shaped organ. We can see off the greater curvature of the stomach is the greater omentum. And on this inside edge, we call this the lesser curvature of the stomach. There's a connective tissue, again, called the mesentery. It doesn't have adipose in it, so it's much clearer. Almost looks like just literally a saran wrap sheet. But it goes basically between the stomach and the liver, and it helps to support the position of the stomach adjacent to the liver. Okay, so this is called the lesser omentum. All right, so it's just another view of that. So here's this lesser curvature of the stomach, and here's this lesser omentum helping to attach the stomach and stabilize it in its proximity to the liver. And here we can see this connective tissue coming off the greater curvature of the stomach, and here they're trying to open it up so you can see that transverse colon underneath. So there's that transverse colon and the greater curvature of stomach being the attachment point for the greater omentum. All right, now we're going to look at some of the mesenteries associated with the liver. The liver is a very heavy organ. It's the single largest abdominal cavity organ, weighs about 3.5 pounds. Majority of that weight is actually coming from the structure of the stomach of the liver. So it's a very solid organ. It doesn't have a big space inside, except for small gaps and spaces for blood to flow through it as it's filtering and metabolizing nutrients. So it's a very thick organ, and literally is going to be adhered to the undersurface of the diaphragm. And we see that the liver is actually divided into a right and left liver lobe by a really thick mesentery that has a ton of collagen fibers in it to help really well support this very heavy organ. So we're going to start to call it a ligament. So technically, this ligament that bisects the liver into a right and left side is called the falciform ligament. A falciform, or falcis, it means sickle. So it kind of looks like a sickle that you would use in the field to cut wheat or something like that. So imagine a nice sickle here, that's the falcip. And that's kind of the shape of this. It kind of has this sickle shape to it. The falciform ligament runs perpendicular to the diaphragm and literally cuts the liver into a very large right liver lobe and a small left liver lobe. Now this is right actually down the body's midline. So if you were looking, you would find the heart would be sitting right above it. And then you'd have sitting right below, imagine this would be where the linea alba was, right down to the umbilicus. So this is right on the body's midline. The liver sits more to the right side. And so this falciform ligament is on the body's midline, but it unevenly divides the liver into a large right liver lobe and a small left liver lobe. This thick connective tissue here, this is the falciform ligament, runs perpendicular relative to the diaphragm and helps to secure this very heavy organ to the undersurface of the diaphragm. This thickened bottom edge of the falciform ligament is actually called the round ligament because it is round. And this is actually a remnant of one of the fetal veins that would be carrying blood from the mother to the fetus from the umbilicus. So I have here the round ligament, also referred to as ligamentum teres. Remember the term teres means cylinder, so that's why they're using that term teres, because it looks like a cylinder. And again, it's a remnant of the fetal umbilical vein. All right, so one of the next mesenteries is called the mesentery proper. It's one of the single largest mesenteries because it's going out to all those loops of small intestine, of which we have about 20 feet. So this is what's going to help secure the small intestines to the dorsal body wall. And it's also going to house a tremendous amount of vasculature going into the small intestine and then carrying blood out of the small intestines with all of the absorbed raw nutrients toward the liver. So in these drawings, they're trying to show you the mesentery proper. So down here, this is all mesentery proper going out to the small intestine. And going out to the small intestine, you kind of see out here, this is the mesentery proper. Okay, so if you grab the intestines and tried to pull it out of the body cavity, you can't because this mesentery is going to attach it to the dorsal body wall. Now there's also a mesentery of the colon, so that large intestine with the ascending transverse and descending sigmoid colon. We're going to see that's also going to be attached to the dorsal body wall and serves the same function as we'd see for the mesentery proper. So here they're drawing you the mesocolon or mesentery of the colon. All right, so this is really nice sort of sequence drawing where they're showing you a successional dissection. So this is if you just opened the abdominal wall, this is what you would see. So this is a little piece of the falciform ligament. Notice here, this is the xiphoid of the sternum, so it is right down the body's center or midline. We see the right and left liver lobes, so there's that falciform ligament. This actually is the stomach, and we can see coming off the greater curvature of the stomach and a little bit underneath, if you kind of look through it, that's the transverse colon. So this is the greater omentum. If I reflect the greater omentum, I now can see clearly the transverse colon, the ascending colon, the descending colon, and all of the small intestines that are inside that framing of the large intestine. And then I can start pulling on stuff, and I can pull the small intestines partially out of the ventral body cavity, but it's going to be secured with this mesentery proper. And same thing is true for the colon. We can see that mesentery of the colon there, or mesocolon. All right, so next is looking at the diaphragm. I still have to go in and see if I can video. We have a really amazing dissection of the diaphragm. But the diaphragm is this dome-shaped muscle. It runs the contours of your ribs. So if you think about, if you go down to where your, maybe your 10th and 11th ribs are, way down at the base, and then you kind of come up towards your sternum, your diaphragm runs that curvature. So it's a dome-shaped muscle. It is attaching to the outer edges of your rib cage all the way around. And then it's attaching into itself in what we call the central tendon. The central tendon is an aponeurosis, so it's a center area. So the fascicles of the diaphragm are almost like rays of sun coming off this central thick aponeurosis. Okay? Now, in that central tendon, we're going to find spaces or gaps to allow for some really important structures to navigate from the thoracic into the abdominal cavity and from the abdominal cavity into thoracic cavity. So there are three major things that have to pass through the diaphragm. One is going to be the esophagus, right? So that foot-long tube that is carrying ingested substances from the mouth to the stomach has to move through the diaphragm. That'll go through what we call the esophageal hiatus. It's actually going to be a break in or a gap in the diaphragm's skeletal muscle. We also are going to have a gap for the aorta. The aorta is the blood vessel carrying blood away from the heart and toward all of our organs and tissues down in past the diaphragm. So that'd be past the, or down in the ventral body cavity, in the abdominal pelvic and the lower extremities. So that very large vessel is called the aorta. And so the aorta has to pass through the diaphragm. And then all of the used blood from all the organs and tissues have to pass through the vena cava, which is a very large vein carrying used blood back to the heart. And that has to go through what we call the venocaval foramen. So these are three large passages through essentially that central area of the diaphragm. All right, so this is looking, if you were looking from the ventral body cavity, the abdominal pelvic cavity, you're looking at the undersurface of the diaphragm. So you're sitting essentially where your intestines would be looking up. This is the view you would get. So here are the outer edges of ribs. Oops. The outer edges of the ribs. So here are the ribs on the outside edge. This is the sternum up here, and you see the ribs on the other side. And this is the vertebrae in back. So if we were kind of looking up at the undersurface of the diaphragm, you see this kind of upside down heart shape. That's the central tendon. And in the central tendon, you're going to see a big hole here. Okay, that's the vena cava foramen. So that's what this is, the inferior vena cava foramen. Remember, foramen is a hole. And then here we see there's two gaps in the diaphragm. One is going to be for the esophagus. That's this guy. And then the other gap is going to be for the aorta. So that's this one. The aorta is a really important pressurized vessel carrying blood to all the organs and tissues below the diaphragm. And so this has to run in a very protected path. So it's basically hunkered right up against the vertebrae. It's the most protected and safest pathway down the dorsal body wall. Remember, in this abdomen, there's nothing bony in front, so you want to make sure that the aorta is as close to the protective pathway of the vertebral column as possible. So that's why we're going to see this aorta way back here, and it's going to go through what we call the aortic hiatus, right? It's like a gap within the skeletal muscle of the diaphragm. And same thing is true for the esophagus. There's a gap or a loop in the skeletal muscle of the diaphragm. These are, again, just really nice drawings of the diaphragm. So this was nice because it's kind of showing you the dome shape of the diaphragm, right? So we're going to see it coming off of the vertebrae and all of the edges of ribs around. So sitting inside this dome, of course, is going to be the liver and the stomach and the spleen. Those are major organs that would be sitting there. This is, again, looking at that inferior view. So we're standing essentially where the intestines would be and looking up. And again, you're going to see this upside down heart kind of sits there. That's the central tendon. This hole here is for the vena cava. So that's the vena cava foramen. We're going to see two gaps, one here and one here. The one that's most protected, this is for that pressurized aorta carrying blood from the heart to all our organs below the diaphragm. So this is the aortic hiatus, and this is the hiatus for the esophagus. And then this last view, this is looking from the heart's view down. I really like this view because not only can you see the central tendon, so this is that thick connective aponeurosis in the center of the diaphragm, but you can see the footprint left by the heart. The heart literally sits on top of the diaphragm and it's laying over on its side so that it can be right over where that vena cava foramen is. So the vena cava is carrying used blood back to the heart and it's going into the right atrium. So really the right atrium is going to lay down right on top of that vena cava foramen. And so that's what we see here. So there's the vena cava foramen. This is the space for the esophagus. So that's the esophageal hiatus. And back here, right in this most protected pathway, right down the front of the vertebrae, that's the aortic hiatus. Okay, so now we're going to look at the liver. Again, the liver is the largest abdominal organ. It's insanely important for the homeostasis of nutrients within our body. So it regulates blood nutrients. It's the very first place that raw nutrients from the intestines and stomach go. So large intestines, small intestines, and stomach are all going to be absorbing ingested nutrients and minerals and water. And when those things are ingested and absorbed, they then move directly through the liver, except for the roundabout way that lipids move. But essentially all the blood coming from the small intestines, large intestines, and stomach all move directly to the liver. The liver's job is to take those raw nutrients and start to metabolize and balance them before that blood starts circulating out to our organs and tissues. So it has a very, very important metabolic function. It also does things like it helps detoxify and it stores, in fact, about almost 10%, like 8% of the weight of the liver is actually stored glycogen. It's the place in our body where we store the per organ weight, the greatest amount of glycogen. All right, so it's comprised of 4 lobes. We've already looked at the right and left liver lobes. So again, remember, the liver is actually going to sit on the right side of our body cavity. It literally sits in the dome of the diaphragm. So imagine the diaphragm's coming this way and up and around it. So it's going to sit just on the right side of our body, which means that the falciform ligament, which we see right here, this is at the midline of the body, right? And it's this nice perpendicular arrangement between the diaphragm here and the falciform ligament here. The falciform ligament doesn't cut the liver in half. It cuts it into unequal sides. It cuts down the center of the body, but not the center of the liver. So the left liver lobe is just to the left of the falciform ligament. The right liver lobe is just the right of the falciform ligament. And then we have two smaller lobes that sit underneath called the caudate that sits behind. Caudal means back. And the quadrate, because it's kind of a four-sided lobe. Now these are smaller and a little bit less obvious. The reality is they don't do anything different, metabolically than any other area of the liver. So the anatomical differences don't really make much difference in the sense of what the organ is doing physiologically. All right, the gallbladder is going to be a structure. It's an organ that sits just underneath the right liver lobe. It looks green because it's storing bile. Bile is pigmented green. It's actually a breakdown product of hemoglobin. So if you think about when you get a bruise and you have a broken blood vessel, blood, when it's oxygenated, is very red. And then as it becomes more and more deoxygenated, you remember if you ever seen a bruise, it starts to get black. And that's the deoxygenated blood. It gets really dark, kind of purpley, and looks kind of black. And then when the bruise starts healing, it turns green. And the reason it turns green is because the body is already starting to turn over that hemoglobin. And the turnover product of hemoglobin, which is called bilirubin, is actually green. And so that's what we're going to see is being processed into the gallbladder. So it makes it look really green. It kind of stains it green. So the gallbladder is a temporary storage structure for this excretory product. It's really a breakdown product of hemoglobin. But one of the great things about it is that it is going to be utilizing a molecule called glucuronic acid that helps it become soluble. And in doing so, it's going to be used to help break down our lipids. So we're going to use it as part of digestion, even though what it really is just simply a waste product. So the bile, which is produced from the liver, is then going to be stored in the gallbladder until we have a meal that has a fair amount of fat in it. And then it gets released to help emulsify and break down fats. So the duct structure associated with the gallbladder is named according to liver. So you'll hear this term hepat, which means liver. We're going to start off, and I'm going to show you these first, and then I'll come back to the text. So this is looking at a nice drawing of the right liver lobe. So this is the right liver lobe here. Actually, let me change the color so you guys can see it a little bit better. So if I blue, so this is the right liver lobe here. Okay, so this is right. And this over here is the left liver lobe, left. Right? The right and left liver lobes are both making bile. And so we can see here, these are little ducts that are going to be collecting bile from the right and left liver lobes. So we call these the right and left liver ducts, but we say it with its Latin term. So we'll say the right and left hepatic ducts, right? So hepat means liver. Oh, that looks horrible. But so we have the right and left liver ducts, or right and left hepatic ducts. And so those are these. There's one on the right and one on the left. So those are the hepatic ducts. So right and left hepatic ducts. We then are going to use a cystic duct, and the cystic duct is going to drain the gallbladder. So here's the cystic duct. Right? There's the cystic duct. That drains the gallbladder. So this is the gallbladder. Okay, I should say empties and fills the gallbladder. So there's the gallbladder. Okay, we're going to use the term common anytime we see two ducts uniting. And so right, I see green. Oh, there it is, green. Right here, where the right and left hepatic ducts come together, we call this the common hepatic duct. So that's the common hepatic duct. Okay, and then when the cystic and the common hepatic duct come together, we call this the common bile duct. So we have the common bile duct in yellow. That's the common bile duct. We have the cystic duct in magenta. Right, so this is the cystic duct. This is going to be draining and filling the gallbladder. We have the common hepatic duct being this portion that's the union between the right and left hepatic ducts. And then we have the right and left hepatic ducts. Okay, so to me, this always forms kind of like a double Y. So I have a Y here. So these are going to be my two hepatic ducts and my common bile duct. And then I'm going to form another Y here. And this is going to be the cystic duct and the common bile duct. Okay, so this is the gallbladder. Okay, so these are the hepatic ducts. This is the common hepatic duct, and this is the common bile duct. And the reason it's common bile is because it's receiving bile from the gallbladder and the liver. Okay. All right, so if we go back again, we have the gallbladder as storing bile until it's needed for digestion. We have the common hepatic duct, which is going to be receiving bile from the right and left hepatic ducts. Remember, hepat just means liver. The cystic duct, that is going to be essentially draining and filling the gallbladder. And then the common bile duct, we say common when we have two unions of two ducts. So here we're going to be uniting the cystic duct and the common hepatic duct into the common bile duct. So we have bile coming from the gallbladder and the liver. All right, so this is a really nice drawing where they kind of cut things open. So again, if we look here, I can start off with my two hepatic ducts. So this is the right hepatic and the left hepatic ducts. Those two ducts are going to unite into the common hepatic duct. So the common hepatic duct is going to be this portion, right? Common liver duct, another way to say it. And then I have my cystic duct, right? That's going to be uniting or coming off, I should say, the gallbladder, right? And then when I have bile from both the gallbladder and liver uniting, I'm going to call that the common bile duct. Now the common bile duct is going to come all the way down to the duodenum, and it's actually going to be releasing bile into the duodenum through what's referred to as the hepatopancreatic ampulla. Ampulla just means a chamber, so that's this little chamber right here. And the pancreas is also going to enter into the duodenum. If you have a break in the intestinal wall for the entry of these ducts, you might as well have only one break rather than two. So we're going to find that the pancreatic duct and the common bile duct are going to come in to the, maybe I'll do white. Are going to come in, well, that didn't really do well, are going to come into the duodenum at the same location. So what do I not have? Well, red, no, green, blue, cyan, I guess. We'll try that one. That works. All right, so that's the pancreatic duct right here. And the pancreatic duct and the common bile duct are going to join together. And so that's what we call it the hepatopancreatic ampulla. This is chamber. And then you have a little sphincter there that allows the fluids from these two places to get released. So when you are eating and you have distension of the stomach and the biochemistry of the ingested substances warrant a release of bile, you're going to see that the hepatopancreatic sphincter will relax, and you'll see contents coming from the common bile duct and the pancreas enter into the small intestine there. Okay, so this is a photo of a cadaver isolated. digestive structures. I actually have this in video form as well. So I took a video of these organs and tissues, so you want to check that as well. But if we're looking here, this is the gallbladder. You can see we're looking at the undersurface of the liver. So this is the right liver lobe, all of this. Okay, so right. This is the falciform ligament, so this is the left liver lobe over here. I can see the cystic duct right there. I can kind of maybe see the common hepatic duct up there. And then this is the common bile duct. Okay, they're showing us the pancreas. So I can see the pancreas right here as well. So this organ, it kind of looks lobulated like cauliflower. This is the pancreas. I can see really nicely the pancreas. The pancreas is about 20 centimeters long. It's actually a quite big gland. It goes all the way across our torso, from the left side all the way over to the right side. And then it kind of sits in this curvature of the duodenum. So now they've cut the duodenum open here so I can see inside. I see a lot of green in here because of the bile remnant within the duodenum. I can also see plicae circularis here, so I can see inside. They've cut the inside, or they've cut the outside open so we can see inside of it. Okay, so this is a nice C shape of the duodenum. All right, so next is the stomach. This one I covered in lecture as well, so it's pretty straightforward. We want to make sure that we can identify the different regions of it. So of course you have the lesser curvature, this inside medial curvature. I have the greater curvature out here. This is all we call the greater curvature. The esophagus is coming in, so this area around here, that's the cardia. Then I'm going to have the fundus being this area to the left and above where the esophagus comes in. The majority of this is going to be the body. And then I have the pylorus being this kind of thicker area of muscle right before the exit into the small intestine. All right, so I can see ruga here. I can see the 3 different layers of muscle. So I have this middle circular, I have the outer longitudinal, and I have the inner oblique now. All right, and this another view. This is a cadaver image, so they're trying to show you the different areas. So again, we have the fundus over here just to the left and above where the esophagus is coming in. The esophagus doesn't come in the top of the stomach, but rather on this medial border of it. So we have the fundus, the cardia, the body is the main chamber. Again, you can store easily up to 1 liter of ingested substances in the stomach at a time. It takes about 2 to 4 hours to move contents through, depending on the distension or amount of fill and the chemical composition. If it's more fat, it's going to take longer to move through. All right, and then we have the pyloric area, which is going to be this thicker area as we start to approach the small intestine. So the small intestines or the duodenum would really start about here. And you have this nice approximately 10 inches that is duodenum. Okay, this actually is a cat stomach. So when we did cat dissections, we could cut it open and look at the rugae, but they go the same in cat as they do in human. It's this longitudinal folding, so going down the length of the stomach, okay? This is a cadaver image. They've actually cut the left liver lobe off so we can see better the stomach. So you can see here the esophagus comes in right down the midline, and you can see it turning a little bit toward the left, and the stomach kind of lays in this space just to the left of where the liver is. Okay, so we have this J-shaped structure that comes back and around to the right side, where we're going to then start to form the duodenum. All right, the pancreas is very lobulate. It is primarily an exocrine gland, so it makes primarily secretions that go into the duodenum through the pancreatic ducts, but it also is endocrine, so we'll talk about that a little bit later, but it makes insulin and glucagon and things like somatostatin. So major endocrine structure as well, but the majority of secretion is actually going to be exocrine. for the digestive system. So it is rather large. It starts over on the right side of your body in this internal curvature of the duodenum. So this is kind of the C of the duodenum, and the pancreas kind of sits with what we call its head in that C of the duodenum. So if I use maybe cyan, so this is what we refer to as the head of the pancreas, and then it's going to travel toward the left side of the body underneath the stomach. So they've cut here right at the beginning of the body of the stomach. So the stomach is actually going to sit in front of it. So it kind of sits behind it and underneath it, and it travels all the way over to the left side. The tip of the pancreas is quite blunt, and it literally points right at the spleen. It's one of the easy ways to tell that you're looking at pancreas when you're dissecting. All right, so it's just another view of the pancreas. Again, you're looking for this kind of dull, whitish, a solid, lobulated gland that sits in this inner curvature of the duodenum. It lays in mesentery, so it's really nicely kind of sandwiched and adhered to that dorsal body wall. And then all the way over here, the tail is going to point to the tip, or the tip of the tail, I should say, is pointing to the spleen. Okay, and the spleen we'll look at in just a second is a lymphoid structure. It's not actually part of the digestive system. All right, and so this is a cadaver image, and they're just highlighting in yellow there the pancreas. And they actually cut off some of the lobules so you can see a little bit better the pancreatic duct. So here's the pancreatic duct kind of running down the length of the pancreas. All right, the spleen, although it's not part of the digestive system, I kind of throw it in here just because it's a large and obvious structure, and it's sitting right next to the pancreas and the stomach. It sits right in the curvature of the diaphragm on the left side. It sits a teeny bit below the edge of the bottom rim, so it sits right between the 9th and 11th rib. Its primary function is going to be immune. So it functions to initiate immune responses. It's filled with a lot of white blood cells. It's also involved in breaking down hemoglobin as red blood cells are turned over. So it's about 11 ounces, and it kind of looks like a kidney, which we'll look at in our urinary section. But it's solid and dense, and it doesn't have an inside concavity like we'll see the kidney does. All right, so this is looking at the abdominal space in a cadaver. And again, on this one, it's kind of nice because you can see just how large this liver is, and it's sitting right underneath the diaphragm. So the diaphragm is sitting in this kind of dome shaped here. They've peeled it back. So there's the diaphragm up there. This is part of that falciform ligament. So it comes off the midline. And then this is the left liver lobe, kind of sitting over where the stomach is. So this is the greater curvature of the stomach right there. Okay, kind of coming this way. We have greater omentum sitting here over the transverse colon, so you kind of can't see that. But way on this side, this really dark structure kind of tucked underneath the ribs on that side, that's the spleen. Okay, almost done. Small intestines. Again, you have about 20 feet of small intestine. It's going to take usually 6 to 8 hours to move all the way through the small intestines. So a meal you had in the morning is going to still be moving through the small intestines by the afternoon. It's divided up into 3 sections: duodenum, jejunum, and ileum. From the outside, it's very hard to tell which area is which. The small intestines from the outside looks all the same. It's about 1 inch in diameter. It has basically the muscularis externa, which is all smooth muscle, and serous membrane covering the outside. So unless you know what it's connected to, it's really hard to tell what you're looking at, meaning duodenum, jejunum, or ileum. So if it's connected to the stomach, obviously we know it's duodenum. If it's connected to the large intestines, we know that section's the ileum. And then the piece of intestines in between is going to be jejunum. All right, so again, here they're kind of looking at the different areas. So on this one, I can see the large intestines over here with the cecum. So then I know that the loops of intestine that are coming out of it, that would be the ileum. Here they're pulling the large intestines up, so it's really hard to see the duodenum because it kind of sits underneath here. Majority of this over here is going to be the jejunum. Okay, so the large intestines is the last piece. So coming off of the ileum, we're going to move directly into the large intestines or colon, sometimes called the large bowel. It's about 5 feet long. And as we come in, we're going to come in on the medial edge. The large intestine is going to start on the right side of your body, and it's going to go up on the right side, across underneath the stomach to the left side, down the left side into the curvature of your pelvis, and then into the center of the pelvis and out. Okay, so we'll have the cecum, which is this blind-ended pouch below where the ileum comes in of the large intestines, which will have a little 6-centimeter diverticula called the appendix, which is filled with lots and lots and lots of immune nodules. We're then going to go up as the ascending colon. The ascending colon is going to turn a 90-degree angle and start going across your body from right to left underneath your stomach. So where it turns, it's called the right colic flexure or the hepatic flexure because it sits near the liver. Transverse colon is going to go across underneath, again, the greater curvature of the stomach to the left side where it's going to go down. It's also referred to as the splenic flexure or the left colic flexure. And then we're going to go down the left side of the body, down into the curvature of the pelvis, so sitting on the iliacus muscle, and it's going to take a distinct curvature to go toward the center. That's called the sigmoid colon, and that flexure called the sigmoid flexure. And then we're going to go straight down through the center of the pelvis, and that's going to be the rectum. So remember, rectus means straight, and so this is the straight part of the colon. Okay, so that's what this is looking at. So just nice ascending, transverse, descending, sigmoid colon with the different flexures. You can either use right colic flexure or hepatic flexure, left colic flexure or splenic flexure. The left colic flexure is always going to be much higher than the right because the liver's on the right side, so we're not going to be able to get quite as high with our colon. So left side's always going to be higher than the right. And then again, the rectum is going to be straight. And this is really just for compaction and storage before we defecate. And this is just a little bit nicer image. This one's nice because we can see the ileum coming in there. That's that last piece of small intestine. Here's the ileocecal valve that's going to help make sure we don't get refluxing bacteria from our colon into our small intestine. They're showing you just a piece of the appendix here, so it's not all of it, so just a little piece of the appendix. So this portion below where the ileocecal valve is, that's the cecum. Above is ascending colon, again, transverse colon, descending colon, sigmoid colon, and rectum, with the anus being the exit. In this one, they've cut open the colon so you can see inside. We still have plicae, but then we also have these really deep folds here. Those are created by the shortened longitudinal muscle. So we have the external longitudinal muscle is going to be a little bit shorter, kind of pulling the intestines into these little pouches we call haustra. So these little pouches here are called haustra. We can see the narrowed regions of the external longitudinal muscle here. Those are called tinea coli. So they're going to create these little compaction pouches. All right, and then this just looking at a little bit closer view of the cecum. So again, this portion here is cecum with the entry into the appendix. Again, the appendix is kind of vestigial, and you can do without it, but it really just houses an extra amount of lymphoid structures, kind of protecting this area here from having too much microbial growth. Again, microbes are going to help us in fermentation. Things that we normally could not digest will be digested and fermented. They help initiate immune responses, and they liberate important vitamins and essential fatty acids for us. All right, and then this again is that cadaver image. The colon basically frames, it's a little hard to tell on here, but frames all of this small intestine in the middle. All this yellow you see, that's just adipose sitting in the mesentery. We're going to see off of the colon, we have these little adipose pieces that help when the colon is moving to help lubricate where the hostra are, and those are called epiploic appendages. All right, and then this just looking again at an open cecum. So here, this is the ileocecal valve. Again, we still have plicae circularis, but the really deep in sort of crevices that we're going to create, or pouches, those are the hostra. This is just out of your textbook. And again, Taenia coli are the reduced layers of the longitudinal muscle. There's actually 3 strips of Taenia coli that are going to pull this colon into hostra, which are those pouches. All right, and then this is just a nice view. They've removed the small intestine. This is a cadaver image where they've cut the small intestine out. So they've cut here. This is the last piece of the ileum. Up here will be the duodenum. And here you can see this is the framework of the large intestine. Up here, this is the greater omentum kind of attaching to the transverse colon here. And then we have descending colon, sigmoid colon, and then the rectum. So you can see how the sigmoid colon kind of sits really nicely in this curvature of the ileum, and the cecum is going to sit in the curvature of the ileum on the other side. All right, and then again, just images of hostra and Taenia coli. Taenia means flatworm, so it really means the flatworm of the colon. And then this is just a nice view of that. So here you can see the 3 areas of reduced external longitudinal muscle. And here they're showing you it on the cadaver. Same thing here, we see on the cadaver, this is the Taenia coli, and it pulls the large intestines into these hostra. As you can see them labeled with the hostra.